Thank you very much. Many thanks to the organizers. I was really looking forward to being there in person. Unfortunately, my visa didn't come in time, and I hope someday visa wouldn't be a barrier for scientists to attend meetings and conferences. That being said, I'm feeling a bit sick, so maybe it's better that I didn't come to spread the disease. So I'm going to talk about computing Lagrangian means without tracking particles. And this is a work that is a collaboration with Jacques Van Est, who is in the audience. So if you're interested, you can talk to him as well later. I'm going to go through this slide very fast because I think everyone in the audience are quite well aware of importance of time averaging in geophysical flows. But we all know that there are separation of time scales in our business. There are like fast phenomena like waves and turbulence, and there are slow forms of dynamics like balance dynamics. And to make meaningful inferences from our measured data or post-process our numerical simulation, we use time averaging quite often. And there are two main types of time averaging that we use. One is Eulerian averaging, where we fix a point in space and we look at the flow variables or the quantity of interest at that fixed point and then average it, or we follow a particle trajectory and measure that quantity along the particle path and then average it. In the next couple of slides, I want to make case for the importance of Lagrangian averaging. One of the main advantages of Lagrangian averaging is removing the Doppler shift. So if we measure things at a fixed point in space, the frequency that we measure for the waves is Doppler shifted. So it's basically the intrinsic frequency of the waves plus a Doppler shift term that make the measured frequency sometimes much smaller than what it is in reality. So Eulerian averaging, which is based on fixed point in space, somehow doesn't capture the intrinsic separation of time scale between the waves and no wave parts, and fails in filtering. An example here is shown I took from Shakespeare et al. It's a part of ocean, and they computed the Lagrangian mean and Eulerian mean, I think, kinetic energy. And they showed that the wave signal stays quite strong in the Eulerian mean because of this Doppler shift, but it's properly removed in the Lagrangian mean version. This is another example. It's a computation that I did using the method that I'm going to present in this talk. I had like a geostrophic turbulence in shallow water system. And then I added a very strong mode 1 wave on top of that and plugged everything to the shallow water equations, let the equation decide the fate of the flow. And then I'm showing the instantaneous value of vorticity to the left in this panel A. And you can see the strong presence of the wave. And in panel B, I took the Lagrangian mean, and panel C, the Eulerian mean. It's quite obvious that both types of averaging managed to filter this strong wave, but the Lagrangian averaging captured the small scale flow features that are blurred in the Eulerian averaging. Again, this is similarly caused by like advection of a mean flow by strong waves, similar concept to Doppler shift. Maybe Hannah was hoping me to talk a lot more about this, but I'm going to skip it very quickly, just mention it. The practical reasons aside, from dynamics point of view or conceptual point of view, Lagrangian means are very important too, because of this. The material conservation of key fields like PV or like scalar concentration or circulation are usually preserved after Lagrangian filtering, but it's not preserved necessarily by Eulerian filtering, which is very important because in a sense, Lagrangian averaging inherits the main features of the dynamics that exist before averaging. If you want to learn more about this, you can go back to the seminal work of Andrew and McIntyre on generalized Lagrangian mean and many other theoretical work afterwards. So if the Lagrangian means are so great and useful, why don't we use them all the time? The reason is they're computationally quite difficult things to do. And I mentioned few difficulties of Lagrangian averaging here in this slide. First of all, particles may get clustered in one region or might be sparse in other regions. So it's really hard to have like a uniform Lagrangian mean field. Second, maybe the most important barrier is the memory. If we want to compute the Lagrangian mean, we usually solve our equations in Eulerian frames. So we need to take time to use lots of variables, velocity and the variable that we want to compute the Lagrangian mean of. And that requires an immense amount of memory because we usually don't keep the fields at high resolution at all time steps. And also it's a real headache when it comes to parallel processing. So if you want to follow particles in space, we usually, when it comes to parallel processing, we divide our domains to some subdomains and solve the governing equations on each subdomain using different processor. If you follow the particles, sometimes the particles may pass from one subdomain to another, which creates a lot of communication between processors, which slows down the computation. They also may get clustered in one subdomain, so this subdomain in the middle needs to compute a lot more things than its neighbors. So considering that everything needs to be synchronized in some step, the whole computation will become much slower. So here I want to present a new approach for computing Lagrangian means that doesn't require tracking particles, which sounds a bit paradoxical. To get there, I need to define a few things and make my notation clear for you. So I picked a definition of average. You can modify it to have more advanced forms of mean. So if I have like a function g, which is a function of time, I compute its mean like this, and then I assign this mean to some time, some slow time. It could be the middle of averaging interval or the beginning of averaging interval, doesn't matter. For just simplicity of notation, I pick the beginning of the averaging interval. And then let's say x sub a, so a is a label for my particle. I need to specify my particle. So I use label a, and then x sub a shows the position of the particle in time. So x sub a t is the position of particle at time t. Then let's say we want to compute the Lagrangian mean of a particular field like temperature, velocity, vorticity, let's call it f. Then the Lagrangian mean is computed using this formula, which is basically evaluating f at the position particle and taking the mean. But this is pretty useless. Maybe not super useless, but it's not super useful either, because at the end of the day you want to have Lagrangian mean as a vector field attributed to some points in space. You want to show Lagrangian mean in your pretty maps, but like Lagrangian mean that is defined for arbitrary labels is not very useful. So we need to somehow define a Lagrangian mean field as a function of spatial variables. And I want to argue that one of the best choices is to pick the mean position of the particle and assign the Lagrangian mean to the mean position of the particle. Some of the advantages of this choice was mentioned in the previous talk by Han. So just to formulate that, so I define my mean position with this integral. Basically, I took the position at different time in my averaging interval and compute the mean. And I use the displacement field that, again, I think Han used in her talk as well, so which maps the mean position, which is not necessarily on the particle trajectory, can be anywhere, to the position of the particle at a particular time t. For example, now at time tau plus t, which is the end of my averaging interval, this ICSI maps the mean position to the position of the particle. And then I use generalized Lagrangian mean, the definition of generalized Lagrangian mean, which assigns the Lagrangian mean of this particle trajectory to this mean position, which I showed with x bar L. So basically, I explained with mathematical formula what I described earlier. Maybe skip this slide. Before presenting my actual approach, I need one more set of definitions, and those are partial means. So I define my partial means to be more or less similar to the Lagrangian means that I defined earlier, but for the averaging intervals that start from tau, the beginning of my original averaging interval, up to some intermediate point between the end and the beginning of the averaging interval. So I call it time t. So my mean position, or my partial mean position at time t, is the position of particle from tau all the way to t. So this bit of the trajectory. Likewise, the Lagrangian mean at time small t is the Lagrangian mean of trajectory from tau all the way to t. Obviously, if I put tau plus t instead of these small t's, I get my original Lagrangian mean fields or Lagrangian mean position for the period that I intended. After some mathematics that I'm going to skip for obvious reasons, I guess these set of PDEs for the partial mean field. Basically, by solving these equations, I get the partial mean field at any point in time. If I integrate these PDEs from time tau all the way to tau plus capital T, I can drive for example, f bar at time tau plus capital T, which is my Lagrangian mean that I was looking for. This is pretty nice because now these fields, first of all, you can just replace this x bar, which is a dummy variable, with just random like x. You can solve these PDEs in parallel with your governing equations. So for solving these PDEs, you only need the instantaneous velocity and the instantaneous value of like field that you want to find its Lagrangian mean, and then you don't need to save any time series. You can do this with solving your Navier-Stokes or Boussinesq equation, and even you can take like coarser time steps because these are like mean values. They're devoid of those fast oscillations. So this is one of the strategies that we offered. There is another strategy that leads to a separate set of PDEs that can be found in this preprint, and each strategy has its own advantages and disadvantages. And then my earlier work was a discrete version of the other strategy that I don't have time to present here. So if I want to summarize the advantages of this new approach, is one of them is much more memory efficient because these PDEs can be solved on the fly or online with the governing equations, so I don't need to save time series of my variables. I discussed in this paper that like depending on discretization of PDE, but this might require much less computational operations than the traditional particle tracking. And it's definitely more parallel processing friendly because you're basically solving PDEs similar to your governing equations. So whatever you do for your governing equations for parallelization, you can do exact same things for these PDEs. Also deals much better with the boundaries. For example, if you have data, for example, it's a region in the ocean. If you want to do particle tracking, the particles may leave the domain, new particles might enter, then you need to do a bunch of funny things like masking. But if you solve these equations, because these are advection equations on this domain, as long as you give me the data inside the domain and the velocity and the field of interest on the boundary of the domain, I give you the Lagrangian mean field in the entire domain. As I mentioned, we offer two strategies, and each one of them has a set of advantages and disadvantages that is discussed in the preprint I mentioned. If I have time, maybe I don't know. I can go through an application of Lagrangian averaging very quickly. If I don't, I can take questions. Okay, great. So one of the things that like GLM theories predicted in past was that geostrophic balance, which we are all familiar with, holds in the presence of very strong waves as long as we have separation of time scales for Lagrangian mean quantities, but it doesn't necessarily hold for Eulerian mean quantities. Something that I mentioned before as well, that Lagrangian mean fields inherit a lot of dynamics that existed for the fields before averaging. This is an example. I had like a vortex. Again, it's a shallow water system, and I added like a wave on top of this vortex, which was a strong wave, and I computed the Lagrangian mean Coriolis force, which is shown with black arrows, and the pressure gradient or height gradient, which is shown by the magenta. So in the left, I'm showing the Lagrangian version of these two, the pressure gradient and the Coriolis force, and in the right, I'm showing the Eulerian fields. You can see in, the Eulerian fields, the Eulerian Coriolis force and pressure gradient don't balance each other at many points in this space, but the Lagrangian version holds much better. This is another example that I mentioned at the beginning of my talk. So I took like a Poincare wave of mode 1 and a geostrophic turbulent field, and I plugged them into the shallow water equations, and I did the Lagrangian Eulerian filtering, and I managed to preserve a lot of important dynamics in the Lagrangian mean field, which I couldn't in the Eulerian mean field. So in short, I offered two strategies leading to two sets of PDEs. Maybe I just offered one of them here, but I told you there's another one. For finding Lagrangian means, they can be solved with numerical scheme of your choice, which can imitate the numerical scheme of governing equation. They have several advantages over particle tracking. I hope this leads to further adoption of generalized Lagrangian mean in atmospheric and oceanic sciences. If you're more interested, you can read about it here. In future, I'm hoping to implement these methods in 3D models. So far, I just did like a toy example, a shallow water example. Hopefully, I can convince the community better when I pick more complicated models. And also implement different numerical schemes for solving these PDEs and analyze the different numerical approaches. And I'm also hoping to improve the Lagrangian filtering by modifying the definition of the mean. So I picked the most basic definition of the mean, which led to the PDEs that I showed you. But you can tweak that definition to get like more advanced filtering, like Gaussian filtering or high pass, low pass filtering. And then these equations are a bit unstable because they're force advection equations. So with some stochastic interpretation, maybe we can add stabilizing diffusive terms. And ultimately, we can use Lagrangian means for subgrid parametrization, considering that what is left after Lagrangian mean is dynamically very useful. Thank you very much. I'm happy to take questions.